We're going to continue our investigation of ordinals, summarizing their properties, and we're going to consider the Burali-Forti paradox. And then after that, we will look at some concrete examples of ordinals given by taking just sums of orderings, basically patterns. The first thing we're going to do is consider this classification theorem for Weld orderings. So the idea is that we've seen that Weld orderings, they're either isomorphic to each other, or one is isomorphic to an initial segment of the other. So we have equivalence classes of Weld orderings, all of those which are also isomorphic to each other. And then there's an equivalence class perhaps of longer Weld orderings, all of which are isomorphic to each other. And the idea is that in each equivalence class, there is a nice member of that equivalence class, which is an ordinal, transitive set well ordered by epsilon, to which every element in that equivalence class is order isomorphic. So in a way, what an ordinal does is give us a canonical way of picking out a nice element from each equivalence class of well orderings, all of the same length. So we'll call the length of an ordering its order type. And basically, that is the ordinal to which the well ordering is isomorphic. And that'll be our first definition today. And then our next theorem will be the classification theorem for well orderings. So turning to the notes, we're at definition 321, 322 on page 29. So 321. So this is essentially is notation. If I've got a well order, and I'll just write that as a member of WO as an abbreviation, then the order type of X with its curly less than is the unique ordinal that it's isomorphic to. So the unique ordinal isomorphic to X curly less than. And the last theorem, 320, the representation theorem for well orderings, justifies this. It says there is a unique ordinal isomorphic to any well ordering. So this is justified by the last theorem, which is 320. And the corollary, again, of that theorem, 322, so I'm calling this the classification theorem for well orderings. So given two well orderings, so I'll just abbreviate that with W orderings, right? So then we all know what that means. So I've got A with one less than and another B with its less than prime here. Exactly one of three things holds. So either they're isomorphic, or one is isomorphic to an initial segment of the other. So I'll just say there's a little b there in big B. So A is isomorphic to this initial segment of B. So the B ordering looks longer, or the other way around. There's some little a in A, where this initial segment of A is isomorphic to all of B with its ordering there. And how would you justify that? Well, again, it's the last theorem. The last theorem says A and B are isomorphic to two ordinals, X and Y, respectively. So these are the unique ordinals isomorphic to first A and then B, respectively. Perhaps via maps, F and G. So I've got something like F is taking epsilon. This is isomorphically to A. And I have G going from Y epsilon isomorphically to B, like this. Now, we've already shown that any two ordinals are either isomorphic or one is isomorphic to an initial segment of the other. That was the classification theorem for ordinals, 316. By theorem 316. Either X epsilon is isomorphic to Y epsilon, in which case, what have I got? This is isomorphic to this. So that means this is isomorphic to this, just by composing the maps. Or X epsilon is isomorphic to an initial segment of Y epsilon. So in which case, I can think of now either for case one here, I can think of first having I can find a map making A isomorphic to B here, right? By first looking at F to the -1 and then composing it with G to send it into B here. That G composed with F to the -1 sends A either isomorphically to B in case one, or an initial segment of B, case two, and case three is because B is longer than A, so we'll G to the, oh, I just said this the wrong way around. No, I go from A here to B. So when, yes, no, that's fine. I'm worrying unnecessarily. Case 2, I do g to the minus 1 takes b to y, right? But y is then an initial segment of x here, so I compose that with f here, and that's going to take b less than prime isomorphically into some initial segment of a. Which is for case 3 here. Sorry, punctuation. Right? Okay. Right. So these 3 cases, which one holds depends on the comparative lengths or the order types, right, here of x and y. The sizes of these ordinals here determine which of these 3 cases is going to hold up there at the top. Okay. So we now get a complete picture for well orderings as well as for ordinals. Any 2 well orderings are either isomorphic or one is longer than the other. B is longer than A, or here A is longer than B. Now we're going to again introduce some more notation. For ordinals, we're going to use from now on lowercase Greek letters. So definition 323. We're going to let ON denote the class of ordinals. For alpha and beta in ON, so here I'm saying these are ordinals, alpha and beta, transitive, well ordered by epsilon. So we're going to write alpha is less than beta if and only if alpha is a member of beta. So compare what we did with natural numbers. We did the same thing. We replaced or said that we could speak of epsilon as less than. And we're clearly going to write alpha is less than or equal to beta if and only if alpha equals beta or alpha is less than beta. So in the next subsection, we talk about some properties of ordinals. We summarize at the top of the page, page 30, basic properties that we've deduced so far. Right? So what we have shown so far about ordinals. Okay. So this is section 3.2. Properties of ordinals. So let's consider this. So let's take alpha, beta, gamma as ordinals. Each ordinal we know is transitive, and epsilon well orders any ordinal. If alpha is a member of beta is a member of gamma, then alpha is a member of gamma. That's just saying gamma is transitive. Right? But in terms of the less than, we've just defined if alpha is less than beta, beta is less than gamma, alpha is less than gamma. So it shows that the less than ordering is transitive. If I take an element of an ordinal, then we showed that every element of an ordinal is itself an ordinal. And moreover, it was the initial segment that it itself determines. So X is the initial segment of alpha under epsilon that the element of alpha determines. So it's both an element and a subset, of course, because alpha is transitive. We showed that if two ordinals were isomorphic, then actually they are the same set. Right? So this is important. Right? And we also showed by the classification theorem on ordinals exactly one of alpha equals beta, alpha is less than beta, or beta is less than alpha holds. So we've got a transitive ordering and it's connected. So it's a strict total ordering. Right? The sixth property is something yet to prove, is principle of transfinite induction for ordinals. So this is number 6 on the list. For ON. So again, like these induction properties, you take some well-defined and definite property, of ordinals, and what we're going to do is try and, well, we shall say, suppose for all ordinals, the following holds. If for all beta before alpha, phi beta holds, implies that phi alpha holds, here, then all of this here, this implies for all ordinals, phi alpha holds. So it's the usual thing. Something is kind of inherited upwards. If all your predecessors have the property implies you have the property, then actually all ordinals have the property. So again, this is exactly mirroring what happens for natural numbers for omega here. So what we deduce then from this is that ON is itself well ordered. It's not just each individual ordinal is well ordered, this class is well ordered. Okay, so let's see so parts of this argument are quite familiar. So we're looking at the proof of 6 here, this statement. So we suppose the conclusion is false here. So we look at the class of ordinals which not phi holds. So it's not the case that this class C is empty. Here. Now, actually, at this stage, this point, we don't know that the class ON is well ordered. Right? We know that ordinals are well ordered. I've only just defined the class ON. Right? If I knew the class ON was well ordered, I could say, let's pick the least element of C. And then by the antecedent, I'd get a contradiction. But I can't quite say that yet. I'm not logically in that place. We very shortly will be. Right? But at the moment, we only know that this C is non-empty. Okay, so pick something in C. Pick alpha 0 in Z. Now, I might have chosen, by chance, the least element of C. If for no beta in C, do we have beta less than alpha 0, then of course alpha 0 is the least element of C. Indeed, that is truly obvious. Okay, but maybe this isn't the case, right? So if this didn't happen, then we've got that there are elements of C that are less than alpha 0. There are elements beta in C which are less than alpha 0. As less than is the same as membership, we're going to have that alpha 0 intersects C is non-empty. The alpha 0 we picked has non-empty intersection with C. Now, alpha 0 is an ordinal, so that is well ordered by epsilon or less than. So this is a subset of alpha 0 that's not empty. So this has a least element. And of course, that's the least element of C that we're after. Now, because alpha 0 is in an ordinal, we know that this is well ordered by epsilon. So alpha 0 intersects C has an epsilon least element. Which I call in the notes alpha 1. So alpha 1 is then the minimal element of C. The epsilon least, right? And so less than least, because they're the same thing here. Of C as well. So what have we shown, right? That C there, right, is going to have a least element. Remember what C was. C was the collection of alphas for which not phi held. Hence we have not phi alpha 1, but because it's the least element of C, for beta less than alpha 1, we do have phi beta. If we're assuming the antecedent here, here's alpha 1, all smaller ordinals than alpha 1, phi beta holds, but that's going to imply phi alpha 1. So then by the antecedent assumption, this implies phi alpha 1. So that is in contradiction to the definition of alpha 1. So our assumption that C was non-empty was false. So C is the empty set, and all alphas satisfy phi alpha. So that finishes 6 there. So the argument that we had, I mean, it looks a little bit unnecessary, but it's because we don't know at the beginning that ON is well ordered, right? But the argument I've just given just shows that it does. I could take any C that's a subclass of ON and do the same maneuver here. Pick an element. If it's not the least element, I then apply the fact that I know that this is well ordered to find the least element of C. So it becomes a two-step process. So the argument shows that any class C contained in ON, if it's not empty, then it has a least element. Alpha 1, just as above. Up here, we didn't use any special properties of the fact that C was the collection of these things, right? We were just talking about, in general, a non-empty class C. So not only do we have any non-empty subset of the ordinals has a least element, any class which has, if it's non-empty, will have a least element here. So the ordinals are well ordered by epsilon. By epsilon, or as we were defining it, or by less than here.